So I will introduce the next session, and in particular, I'll just introduce our Senior Director for Research Data Science, Craig Kapfer. And Craig leads the Marlowe effort here at Stanford, and he's going to be leading this discussion on how Marlowe is being used to advance discovery. Craig, take it away.
Thank you, Chris. So, wow, what a turnout. Thank you all for coming. We are very excited about Marlowe and its ability to help various research programs. We have had a lot of interest in Marlowe to start. We've got over 95 PIs onboarded onto Marlowe and over 500 users. The demand is incredible, and we appreciate the support. We do hope to get more computational firepower in the future. We know we're kind of overloaded at the moment. Today, we wanted to highlight some of the research which is being done on Marlowe as a means of showcasing it a little bit. And our first speaker is an expert in computer vision, Klemen Kotar in Dan Yemen's lab. He's going to be talking about counterfactual world modeling, I believe. Is it close enough? Okay, and without further ado, Klemen.
Hi, yes, so I'm Klemen, PhD candidate with Dan Yemen's in computer science, and I'm going to talk about world modeling with probabilistic structure integration, which is sort of a big joint effort of our lab done with all these wonderful people. To begin with, I want to ask ourselves this question: what makes a good world model? And I'm going to make sort of semi-opinionated stance that it requires two things. One, a large pre-trained model, which I think most people would agree with. And this just absorbs all of the data that you could feed it. And then secondly, you require something that we would call a generic prompting interface. So this is sort of a method of extracting the information you want from the model without explicitly retraining it or reconfiguring it for your specific task. Now, we have a very good existence proof of this in the language domain. Namely, our large pre-trained model is one of these GPTs. And then slightly less obvious, the generic prompting mechanism is sort of built in, which is just language. The way you interact with this model, you don't fine-tune it anymore. You don't ask it to do very specific things. You basically just give it a text instruction, and you get the answer out of the model. So the pre-training task is basically just our prompting interface here as well. Now, in computer vision, we do also have the first part of this. We have these vision foundation models, large pre-trained models like CLIP or Dino or Cosmos or Sora, the video models. But what we're sort of lacking is the generic prompting interface. So we can, train linear probes, or we can text prompt it, but the text isn't really as expressive as many vision tasks require. And so there's no native prompting mechanism. We can examine why that is. So one view of looking at this is through putting all the tokens on a token quality pyramid. And if you think about it, text is really, really towards the top of this because it's compositional and abstract and contains these real-world concepts in a very compact form and has roughly the same amount of information content per token. And it's just very, very, very flexible. And you can prompt in it very easily. On the other hand, pixels are really towards the bottom because they're sort of almost all of the opposite of text. There's too many of them per second of input stream. They contain way too few information. They're super redundant, and they don't really contain abstract information. Similarly, you could imagine other real-world inputs like audio being pretty low. Like the fact that you're converting the sounds I'm making into words is like a really complicated processing pipeline that your brain is doing. So then you can say, okay, maybe you can tokenize and auto-encode, compress the images a little bit to get a slightly higher quality input, like an image token, but it's still really, really, really far from how good text is. And so you might ask yourselves, okay, how do we obtain better vision tokens from pixels? And here is where we can take some inspiration from neuro and cognitive science. So particularly, people have been studying these ideas of hierarchies that our brain creates to extract these abstract concepts from raw input streams that our eyeballs get, which look kind of like pixels. So one of the first things that we do is we obtain optical flow, which is sort of the motion of the scene. And then we can turn that into segments, so grouping things that move together. And then from that, we can get to 2.5 or 3-dimensional shapes. And from that, we can build higher levels of abstractions like scene graphs and then resolve physics that way. And so there's like classic works from Spelke and Marr about ways that a cognitive model of the brain might do this. But I'm going to talk about sort of our artificial intelligence approach of trying to integrate some of these concepts. So the first thing we're going to do We call it probabilistic structure integration. The first thing we need is a probabilistic next frame predictor. So this is still very much that large pre-trained model, that bitter lessony, just absorb the data. And specifically, we want a model that can take an input image and predict one of several plausible outputs. So the world is really diverse and multimodal. You can't just guess exactly what's going to happen next, but you can model the distribution of what might happen next. So you need a model like this. Secondly, what you need is a way of extracting some structure from this model. So this is basically akin to the visual equivalent of prompts. So you want to be able to, if you have a really good world model, you want to be able to sort of give it a video and just ask it, okay, what happened with this ball, and somehow extract the optical flow, the motion of what happened. Similarly, you might want to be able to manipulate your generations by saying, well, if this little bit of the scene moves like this, what else has to move with it? And so, if you can prompt it to such a degree of precision, you can basically get very clean object segments out of it. And then finally, what we believe is that you should be able to integrate these things that you can extract from a good world model back into your model, just as an additional layer of tokens to give you new interfaces of controllability, new axes in which you can manipulate and figure out what the model, what it is you want the model to do. And so by basically analyzing a scene and sort of reasoning through what is going on, you should be able to improve your prediction quality. Now, in order to implement this, we sort of looked at this new architecture which we designed, which is decomposing the sequence prediction problem into a sequential and into a parallel component. We basically formulate video generation just as next token prediction, but that can be the next frames can be decoded in any order in arbitrary amounts of sequential or parallel. Specifically, the way we do this is we imply a quantizer again to obtain those like low level, not high quality, but first input visual input tokens. And we basically patch up the image into local sections and encode only the local sections within each patch. And then we give the model these pointer tokens, which allow it to jump around during its prediction and predict the image in arbitrary order. See, text is one-dimensional, but images and other data types are higher dimensional. And if we want to do a causal GPT-style modeling approach, we need to be able to arbitrarily jump around the sequence we're predicting. And then we put this into a big LLM-like model, and we train it. The nice thing about our pointer tokens is that they allow several decoding strategies. One of them is just sequential, resolving one bit of the next frame at a time, patch by patch by patch. On the other end of the spectrum, we have fully parallel generations. Now, these fully parallel generations will not be as high quality because the different patches can't agree with each other what they should predict. So they'll predict sort of like rough distributions of next frames, but they give us good snapshots about what the model is thinking as it's generating. And finally, we can do a sort of hybrid approach where we sequentially resolve the most important physics elements of a scene and then sort of switch to parallel prediction for faster inference. So we collect a big data set which contains released data sets as well as some things that we've crawled from the web that include everything from product reviews to city walkthroughs to the data sets that have camera annotation to egocentric data sets and some synthetic data as well. And we train this big model which we call PSI-Psi. And thanks to Marlowe, we can let it absorb all the data and scale it to a very large scale. So now we're going to look at the individual parts of this approach. So first of all, our probabilistic predictions. And here, one of the key things I want to impress upon you is that everything we're doing can be formulated as a specific sequence. So purely by designing the sequence, the prompt which we ask the model, we can control what we're going to get out. So here we can simply design next frame unconditional prediction as, here, I'll give you one frame, and you predict the next one. So we give it this car, and we ask it, give me some plausible predictions, and it will give us some plausible predictions. So sometimes it'll pan, sometimes it'll zoom, sometimes the car will move. But they're all plausible. They're just not really, really well controlled. Now, one way we can impose some more control is by giving it a different type of image where it's more obvious what's happening. The camera here looks like it's sort of a traffic cam, so it's not really going to move by itself. And so just by nature of that, the model is basically learned to basically predict forward motions of the cars and nothing else in this type of example. But we might be able to modify our prompt just a little bit to basically constrain our predictions. So for example, we can take a few patches from the next frame and just give that to the model and have the model predict around that. So in this example, we give it frame 0 and just those little gray patches of frame 1, and it really, really, really tightly constrains the prediction. It even figures out that there's an occlusion here with this tree and hallucinates a different type of wall art from the ground truth that still looks good and plausible, is just not constrained by what we revealed. Similarly, we could constrain motion with animals like this. So here we give it a bunch of patches to constrain the prediction, and then different seeds will generate slightly different predictions. If you noticed here, sometimes it generates foliage in the background, and sometimes it generates a fence, but they're both plausible because we don't know what is being disoccluded here. And we can also ask ourselves what the model is doing internally. So because we can do that parallel prediction, we can ask the logits of every patch and figure out the entropy, so how uncertain the model is of what part of the prediction. And this allows us to sort of iteratively see, as it's reasoning through its generation, how different parts are being resolved. Now that we have this predictor, we can look at how we might extract structure from it. So again, by just constructing new prompts, here we take the partially conditioned prompt template from the first part and add in an additional modification, which is we put a little green tracer on the ball. We can then see what happened to this little ball tracer and basically extract the flow, the track that the ball took in the scene, in the video. And this allows us to track a bunch of points on a bunch of real-world videos with camera motion and object motion and everything. Similarly, we can apply a procedure of modifying just a little bit of an image and seeing what moves with it to get a segment out of it. So here we can sort of manipulate just this little patch here to get the segment of the cup. Here we can figure out how these other parts move together, so the laptop and the Pringle scan, where here we can isolate just this one little butter and get its segment from its motion. Now finally, we'd like to show the power of integrating these structures back in. Because we can just add arbitrary new tokens, we can add, for example, camera conditioning tokens to our prediction and get the model to generate null view synthesis. So this is generated videos based on just that first image, and it basically can figure out how the scene must look if we had a specific camera motion. Or we can integrate quantities we've extracted ourselves, like optical flow, in order to get optical flow condition prediction. So this allows us to obtain things like depth, and it allows us to condition the model with the optical flow as well, which allows us to get very, very sharp predictions of next frames. It also allows us to do arbitrary manipulations of a scene. So we can apply these 4 arrows here and translate and rotate the laptop to get a really, really good prediction of what would happen if we moved it in this way. And here we compare it to some diffusion-based baselines. In the interest of time, I will go over a few more of these a little bit quickly. But I want to showcase one final point, which is that integrating these things significantly improves the prediction capabilities of even the base model, because we can decompose the prediction problem into 2 simpler problems. First of all, the problem of predicting the optical flow, basically the transport plan of the scene, and secondly, the problem of resolving the pixels, the actual sharp image of the scene. This is kind of like decomposing a reasoning problem into step-by-step reasoning in a language model. And so we'll show some examples where the base model, this is our RGB to RGB model, basically made no motion when prompted with this image. And it's not just us. Even Cosmos, which is like an industry model, when prompted with this image, will only do like camera pans, will actually not resolve the physics. But when we do the flow intermediate, the model first resolves, aha, the ball moves, and then actually moves the ball. Similarly, in this example where the ball should roll down the ramp, we can see that Cosmos generates these like camera pans and hallucinates a hand, but through the flow intermediate, we can generate a transport plan and actually resolve the motion. So in short, by having a probabilistic predictor, which is good enough to be able to extract discrete structures from it, we can obtain new tokens, which we can integrate then back into the model to get a very nice, controllable, and realistic world model. Yes?
Integrate additional information. For example, if you knew the likelihood of someone sinking a basket, will that improve your model? Whether the basket shot's going to go in or not.
Yeah, so I think that in general, one of the key things we wanted to do is basically have the model learn just from the data itself. So these flow intermediates and all these extra tokens we've added were actually all extracted just from the raw videos. So, in the limit, if your model watches a bunch of basketball games, it would learn to recognize different players and then adjust its probability based on who is actually throwing the basket. But also, I think in general, this should be applicable to sort of any data. I showed a vision example here, but anytime you have data where the input is not as high quality and not as organized as text, so this could be any sort of time series data or biological data, you could basically use an approach like this to help self-organize the data a little bit. So this is really where we're sort of getting at. Yeah.
What exactly is provided by the flow intermediates so that it doesn't do something like, for example, the ball doesn't jump off the ramp?
Yeah. So actually, good that you asked this question. If you do a bunch of rollouts of the flow intermediate, most of the time it will go down the ramp. Sometimes it actually goes up the ramp because this is just a 2-frame model. We have other models that have 3 frames so they can resolve physics. But in very rare cases, it actually does sort of like roll slightly off the ramp. So it's not completely out of the plausibility of distributions. It just has much, much, much lower probability. And so we actually add no guardrails. We just let it learn the physics from watching the videos itself.
Would your entropy map help in that case, for example?
Yes, you can basically use the entropy map to figure out what is most likely to move. In fact, we have this like intermediate extraction structure, which I didn't show, which is literally called probability of motion. So you can give it images, and you just ask it, what's the entropy of the flow there? And you can basically see what is most likely to move in this scene. And here, this dog is like very likely to move, but the head is more likely to move than the body. So it's like really, really well resolves what could happen. OK, I think my time is up. Thank you so much. Oh. Thank you, the Marlowe team, for supporting us with Compute.